In a lot of science fiction, humans boldly go to faraway stars and planets without much of a second thought. The heroes are able to cover astronomical distances using fictional hyperdrives or teleporters, whereas in reality the speed of light is known to be the ultimate speed limit in the universe. Even at this limit, interstellar journeys would be long. Stars are separated by multiple light years, 1 light year being the distance light travels in a year. People have speculated about how long a more realistic journey would take without any sci-fi technobabble. It's rare though to find a discussion within popular media which is actually motivated by a robust knowledge of physics and relativity. One argument goes as follows. With current spacecraft technologies, it would take thousands of years to reach the nearest star. This means that many generations of people would be born and die during the trip. What is more, it would seem likely that a new, faster spaceship capable of overtaking the original would eventually be constructed, rendering it obsolete. This would make interstellar travel unattractive for the astronauts and for society as a whole. I believe that such a generation ship would be impractical, and in this video I will explain why a crew could make the trip in their lifetimes and ensure that they are not overtaken in reaching their goal. You are probably watching this on or near the surface of planet Earth, where gravity is pulling you towards the center of the planet. Unless you are a skydiver or an oligarch who has accidentally fallen out of a window, there is a floor beneath you exerting the same force upwards. You are pinned to the floor by the force of gravity. If the floor wasn't there to stop you falling and there was no air resistance, the force of gravity would be enough to accelerate you downwards at a rate of 1g. You might have accelerated even more rapidly than this in a fast car, roller coaster or aircraft if you were said to have pulled a lot of G's. One of the postulates of general relativity effectively states that gravity and acceleration are indistinguishable. Being pressed into the surface of a planet by gravity is the same as being pressed down to the bottom of a spaceship accelerating at a corresponding rate, even if it is far away from any sources of gravity. This makes 1g a pretty good rate of acceleration if you're an astronaut on board a spaceship. While accelerating or decelerating, the astronauts would experience the equivalent of Earth gravity. No weightlessness, no muscle loss, and so on. With a much larger acceleration lasting for an extended period of days or more, the human body may not survive such harsh stresses. With a much gentler acceleration, you would never get anywhere. Mathematically, an acceleration of 1g means increasing your speed by 10 meters per second every second, or going from 0 to 36 kilometers per hour in 1 second. So for example, after 1 second your speed would be 10 meters per second, 20 meters per second after 2, and so on. If you did so for long enough, it would seem that eventually you would exceed the speed of light. But there's a catch in the form of Einstein's special theory of relativity. One of its postulates is that the speed of light is the same for all observers. This is actually very strange. Imagine if Alice flashes a laser beam which moves away from her at the speed of light, while Bob is on a spaceship going at half the speed of light in the same direction. Surely Bob must perceive the beam as escaping from him at only half the speed of light again. Well, no, because as the postulate states, the speed of light is the same for both Alice and Bob. The way to reconcile these facts is that Alice and Bob perceive time and space differently. One consequence is that even when an object is experiencing what it feels as a constant rate of acceleration, for example if a spaceship's engines are putting out a constant amount of thrust, it will never quite reach the speed of light. So there are two ways to view an interstellar spaceship. Mission control on Earth sees it moving away and getting faster. But as the spaceship approaches the speed of light, the speed levels off. Eventually, the engines cut out and it recedes at a constant speed. Astronauts on board are pretty much stationary relative to the spaceship, but they feel 1g, just like you are right now, until the engines cut out and they feel weightless. Star systems move at tiny speeds compared to what we're discussing here, so I will treat them as near enough stationary relative to each other. This means that a spacecraft must spend just as long decelerating to a stop at the end of the voyage. A typical trip would look like this. Burn forward for a certain time so your speed rises, but never gets to the speed of light, then coast along at this constant speed, and then burn back to come to a stop again. A small amount of distance will be covered during the speed up portion, an equal amount during the slowing down portion, but most of the interstellar distance is covered during the high-speed coast phase. The Alpha Centauri system, actually consisting of 3 stars, is the closest to Earth at 4.4 light-years. Suppose that a spaceship maintained a rate of acceleration of 1 g for an entire year. As a result, the spaceship would be traveling at just over 70% of the speed of light. Factoring in the acceleration and deceleration stages and the final speed, the spaceship would take just under 7 years to make the journey from the perspective of the Earth. This is a pretty reasonable time frame, shorter than many prison sentences. In fact, due to time dilation from traveling close to the speed of light, the astronauts get time off for good behavior. The trip appears to last only about 5 years to them. More on this in a moment. If the ship had enough fuel to only accelerate and then decelerate for half a year each, the trip would take 11 years from Earth's perspective and 9 years from the cruise. Still not too bad. What about somewhere further away like the 82 Eridani system? It's 20 light years away, meaning that even at the speed of light, the trip would take 20 years. For this journey, I would recommend an acceleration time of 3 years to reach 95% of the speed of light. At this speed, time passes over 3 times slower for the spaceship relative to the Earth. In other words, suppose the astronauts decided to have a baby during the trip. This obviously takes 9 months from their point of view, but during the same period, people on Earth would have held 3 annual Oscars ceremonies, which might actually be a downside for the poor kid. The whole trip takes 22 years from Earth's perspective, but only 8.5 for the astronauts. As an aside, once a ship has departed Earth in these scenarios, it will almost certainly not be overtaken or beaten to its destination. With a travel time of under 7 years to Alpha Centauri as seen from Earth's perspective, a follow-up mission could beat it by 3 years at most if technology to travel at light speed were somehow invented. Even if instantaneous teleportation technology were invented the day after they left, the astronauts would still arrive at their destination first. Their 7 years travel time is roughly equal to what I will call 1 unit of DAT, or Denver Airport time. The time from when the city of Denver, Colorado made a preliminary agreement to acquire land to an airport becoming operational. It's also about half a BAT, or Berlin Airport time. Even in the future, large projects will take time to complete, will suffer delays and require bureaucracy. In any case, based on the numbers, I believe that the main necessary and sufficient condition for humans to go interstellar is to have a spaceship which can accelerate at a rate of 1 g for a total of around 1 or 2 years. This is of course much easier said than done, and we are nowhere near the technology to make this happen, but let's have a look at how such a feat might conceivably be accomplished within the known laws of physics. Maintaining 1 g of acceleration is no big deal for a modern rocket. In fact, higher accelerations are routine. The problem is that they only have enough fuel for a few minutes of burn, not for a couple of years. Getting a simple chemical rocket with enough fuel to make an interstellar trip is a problem for the following reason. An ordinary rocket is propelled forward when hot gases shoot out of its engines at high speeds. Every action has an equal and opposite reaction, so the larger the momentum or inertia of the gases going backwards, the more momentum the rocket builds up going forward. Suppose we have a 1 kilogram satellite and we need 1 kilogram of fuel for its final 1 minute burn forwards. What about a 1 minute burn before then? We would need 2 kilograms of fuel, 1 more for the satellite and 1 for the first bit of fuel. We need 4 kilograms for the minute before that, 8 before that, and so on. The amount of fuel required grows exponentially with the amount of time the rocket accelerates for, like the grains of rice on a chessboard. In other words, we need to propel the fuel to finally propel the satellite. This is why rockets are normally staged. A small spacecraft final stage sits on top of a large second stage, which in turn sits on top of a huge first stage. To have enough of our current fuels to keep burning forward for years, the stages would get absurdly large. But there is hope. Let's say that we have a super advanced fuel which gives twice the impulse or kick from the same amount of ordinary fuel in the example I gave previously. This means we only need half a kilogram for the final minute of burn, 3/4 for the last but 1 minute, and so on. So although the fuel is only twice as good as before, the final mass of the rocket is also exponentially smaller. What we want then is a fuel which shoots out of the back of the spacecraft's engines carrying the most possible momentum, because this will give the spacecraft the largest possible push forward. Fortunately, due to relativity again, there is no limit to how much momentum any given piece of matter, such as a grain of sand, a molecule, or a particle, can carry. You could, in principle at least, accelerate a huge spaceship to half the speed of light by firing out just a single atom with an eye-wateringly large amount of momentum. Granted, I can't imagine a technology which would get the job done with just one atom, but we could certainly greatly increase the amount of momentum every piece of propellant carries over current chemical rockets. One place where a large amount of energy, and therefore momentum, is imparted onto matter is a particle accelerator. A big machine, such as the Large Hadron Collider at CERN, can impart 6.8 trillion electron volts of energy onto a proton, which corresponds to a huge amount of momentum. Even with advanced technology, it would probably be impractical to blast the city-sized LHC into space to use it as a rocket engine. However, let's assume that it would be possible to make a particle accelerator which can reach about 1 billion electron volts into a spaceship engine. Now, if you aren't familiar with what this unit of energy means, it doesn't really matter, but to sum up, we want our rocket fuel to have as much energy as possible. The most energy humans have ever given to a piece of fuel, or a piece of anything, is 6.8 trillion in units of electron volts, and I'm suggesting we get a rocket engine which goes to just 1 billion. There are technologies such as laser Wakefield accelerators where particles can reach these energies in a few centimeters of space on top of a laboratory bench, so it's not inconceivable that corresponding space thrusters can be constructed which are small and light enough to be practical. With all this in mind, the ship would have to bring 1.8 units of propellant for every unit of actual ship mass for the 7-year trip to Alpha Centauri. Let's say the mass of the spaceship, the astronauts, life support, whatever equipment they would need at their destination to establish a permanent base, would be 200 or so times the International Space Station at 100,000 metric tons. There would need to be 180,000 tons of propellant. All that's important is how much more fuel is required relative to the spaceship mass. If Private Pyle wants to bring an extra kilo of donuts on the mission, there would need to be 1.8 more kilos of fuel, and so on. So far, this isn't looking too bad from a practical point of view. Note that just as with rocket stages, it's possible to store the propellant in individual tanks attached to the spaceship, which would detach after becoming empty, a bit like the external tank on the old space shuttles. This just means that the mass of the fuel tanks themselves need not be included in the final spaceship mass. While we have the basic technology for the ship's engines, the issue of powering those engines is much harder. The energy itself requires a mass of fuel. That is what Einstein's famous equation E=mc² means. The most energy that can be extracted from a parcel of matter is its mass times the speed of light squared. And that's just the theoretical maximum. Burning releases less than a millionth of this amount, while nuclear reactions release a fraction of 1%. The less efficiently we can extract energy, the more massive the spaceship gets, which in turn means we need to bring more fuel and so on. One sure way to get to the theoretical maximum is to annihilate matter together with an equal amount of antimatter. Half a kilogram of each would release the speed of light squared's worth of energy. Antimatter has been generated on Earth, so we know it can be done in principle. We are just nowhere near manufacturing it in any significant quantity. There are also huge unknown technological issues with storing antimatter and then efficiently using the energy that comes out of it. I have seen other proposals, such as taking a miniature black hole, which is even more technologically uncertain. So in short, storing energy close to the theoretical maximum is at the very early lab stages of development, with perhaps centuries of development ahead. Remember that I ran calculations with each proton having 1 GeV or 1 billion electron volts of kinetic energy? This is significant because it means that one proton is carrying the energy equivalent of a second one. So for every kilogram of propellant which will be shot out of the back of the spaceship, about 1 kilogram of fuel must be turned into energy. Something like a total inventory of 1.5 kilos of hydrogen and half a kilo of antihydrogen. This makes the propellant overall half as efficient per unit mass as before, and this in turn means a more than doubling of the mass of fuel required. In fact, the Alpha Centauri mission would need over 7 kilograms of mass of this propellant fuel mixture for every 1 kilogram of spaceship. And all that is assuming a perfect theoretical efficiency. So I would argue that it might be doable, but certainly difficult and expensive. Another possibility is called a photon rocket, where matter and antimatter annihilate to produce gamma rays. It is then those gamma rays, moving at the speed of light, which fire out of the back of the spaceship to propel it forward. The gamma rays come out in pairs, and at least one of them needs to be redirected for this to work, which is extremely challenging technologically. At perfect efficiency, this would require 5 kilograms of fuel for every kilogram of spaceship. Half is matter and the other half antimatter. In both cases, there are other tricks to make the journey more tractable, such as somehow beaming energy from Earth or from some automated installation in deep space. Imagine, for example, a scenario where a second, slower and fully automated ship full of fuel is sent out ahead of the main ship, crewed by people. The crewed ship doesn't have enough fuel to fully decelerate upon reaching Alpha Centauri. However, the two missions are perfectly timed so that just as the crewed ship runs out of what fuel it does have left, it meets the robot ship and completes the deceleration. You could repeat the idea of staging by then sending out 2 more fuel ships, another one for the colony ship and another one for the first fuel ship, and so on and so forth. Also remember that dumb canisters of fuel or even robotic spacecraft are not limited to a few g of acceleration like living beings. It's possible to fire a beam of individual fuel atoms, possibly antimatter, out of a particle accelerator, or guided canisters out of a long electromagnetic railgun. Things like cannons or railguns involve skull-shattering levels of acceleration, but are much more efficient than rockets, because they don't have the exponential fuel-to-push-fuel kind of problem. Although it would require advanced technology and lots of resources, I believe it's possible to complete an interstellar trip taking a fraction of a human lifetime within the boundaries of known physics. To summarize, squishy humans on board an interstellar ship are limited to accelerate at a rate of about 1 g, which is the same rate that a falling apple would accelerate due to the Earth's gravity. If the ship can maintain that rate for something like a year, remembering that you have to spend just as long decelerating at the end, then it can get to a good fraction of the speed of light. This would complete a journey to the nearest stars quickly enough that the original astronauts would be young enough to set up a colony and have kids. This is also helped by the fact that time dilation would make the journey appear to go quicker for the astronauts. To make that happen, however, you would need technology far beyond what we have available. In particular, the engines would have to be very efficient in terms of firing propellant out of the back of the spaceship, while the power source for them would have to be extremely energy dense. I will put up the relativistic equations on screen and answer questions in the comments. Thank you for watching.